So we actually stop at example number 5. Well, in some cases, again, the normal force, it's only true that the normal force is equivalent to the weight if the object is lying horizontally on a surface. But if in this case, for example, it is somehow inclined, and actually it is inclined 30 degrees from the horizontal, okay, the particular angle there, the normal force is no longer equal to your weight. So I think if we're gonna go revisit, how would you draw or how would you know the location of this angle 30 degrees? Well, if we're gonna revisit that one, maybe perhaps a good view on that. I'll just gonna redraw one here. Like if this is my object, we know the weight of the object will always be going downward, or Fg. Okay. And again, as mentioned, your surface is angled off with uh, 30 degrees. So somehow the surface is, you can think of the surface. You're going to draw your surface, if this is the surface, where the object lies. Okay. So if you're going to measure that particular angle with the horizontal line, so I'm just going to draw a horizontal line. So this is the horizontal line. Which represents this particular part here, the bottom part of your incline. Okay. Then the surface is just represented by the black line. So this is your, again, this is your surface. And then the angle is given by 30 degrees between the horizontal line and the surface. So this is your 30 degrees here. Okay. Remember that drawing your normal line is always perpendicular to the surface. So if I'm gonna draw that one out, it's something like, again, this would be my normal line, or the normal force. Okay. The normal force, again, by definition, we define it as perpendicular, the force exerted by the surface on an object, and it is always perpendicular to the surface. So that means that this is 90 degrees here. If you're going to draw the perpendicularity symbol, 90 degrees. Okay. And if you can see, since your surface somehow is tilted, you would also expect that somehow your coordinate system in this case is being tilted. That means that Fn becomes your perpendicular forces, and anything that is along your surface is your parallel surface. No, parallel force. So we've taken note that you have friction which is going upward. Okay. FF, and your FG in this particular case, you can see, since you can think of this one as your X and Y is also tilted. This is X and then this is Y. So if that is tilted, if you can see, this FG has two components. You have one, I'll just call this one as my FG perpendicular because it's perpendicular to the surface, and the other one is FG parallel. So your FG here has two components, FG parallel. And again, the key thing to note there is how would you identify this angle of 30 degrees? Because in most cases, this angle is the one that is giving at the angle from here. But if you can see, if I'm going to extend my FG, if you can see, this just makes, if I'm going to hit that one to my horizontal line, if you can see here, this is just perpendicular to that horizontal line, this one here. So if it is perpendicular, you're actually making yourself a right angle triangle. So if you can see, this is just a right angle triangle. This whole thing here, this is just a right angle triangle. So if you're given this angle as 30 degrees, well, based on what you know about right angle triangle, this one here is always 90 degrees. And in a triangle, the sum of the angle is 90 degrees. Oh no, 180 degrees. So that means that this angle here is complementary of the 30-degree angle. And complementary angles, if you can remember, the sum of these two angles here, this angle plus this angle will give you 90 degrees. Okay? So that means that this particular angle is 60 degrees. How do I know that one? Well, again, if you can see, I'm making a right angle triangle or the right triangle. Again, I made that one by just extending my FG towards my horizontal line. Again, the horizontal line and the surface, the inclined surface, it makes 30-degree angle. But if you're going to look at that one in, yeah, so that's, again, that you make a right angle triangle. I think this is much easier to see than the one that I suggested last time. So maybe just use this particular reasoning. So that means that the angle of 30 degrees is the other one here. So the 30-degree angle is therefore the angle between your FG perpendicular and your FG. Okay? So for the question of how would you get that 30-degree angle, the location, maybe perhaps you're just gonna draw it this way. I think you're more familiar with this one. You can make a right angle triangle, and again, these two angles here are complementary. That means that their sum is 90 degrees. And if you can see, this FG perpendicular, that's perpendicular. So that means that this is 90 degrees. So that means that this is also 90 degrees. So the sum of that is 90 degrees. So therefore, that 30-degree angle is the same as this one here. So the location of your angle is somewhere here. Okay, any question in this part or clarification?
I just have a comment about the audio. It's pretty muffled.
Oh, hmm. So maybe there's steps. Yeah, I just gonna change the steps. Yeah, I'm just gonna turn. Do you think the previous one, or I mean last meeting, that was better? Oh yeah, was that better?
Yeah, it was
Right now I'm using okay, okay. Maybe I'm just gonna turn off. I'm using a Bluetooth headset. So
oh, okay.
okay, can you hear me now? Hello?
Yeah, it's better.
So this is better. Okay. So any question with this one here? So maybe perhaps just draw it this way.
I think, yeah, I think this is something that you're more familiar with. Again, you can just make a right angle triangle there. So the opposite part, well, that would be the complementary 60 degrees. So remember that if you're making the perpendicular force here of FG, the angle between your FG and that is 30 degrees. So remember, this is quite important because you want to get the components, the vertical component of your, or the perpendicular component of your FG and the parallel component of your FG. And if you can see here, it's actually Fn. Fn is just a portion of your FG. It's not equal to FG. And I believe that that's what we get last time. So the component of your FG is just some sort of, again, that is just uh, trig. Okay, so again, if I gonna somehow, I will have this portion here. If I gonna rewrite that one, that means that my FG is this. That's the hypotenuse. And if you can see, my FG perpendicular is this one here. This is 30 degrees. Okay, so this is my FG perpendicular. And the other one, remember that this FG parallel is just the same thing as this one here. So if you're wondering, where did I get the FG parallel as equivalent to the other side of my triangle? Well, if you can see there, these two are perpendicular. The parallel force and the perpendicular force of components of your weight is just perpendicular to each other. So again, your FG perpendicular is the adjacent side. So therefore you have FG perpendicular is equal to FG cosine 30 degrees. And your FG parallel is, well, if you can see, that's the opposite of 30 degrees. So therefore that's FG sine of 30 degrees. That's what we got here. Okay. And if you're wondering why is it that I didn't solve for the parallel component of the force, well, the reason for that is for this particular question, we're just being asked what is the normal force. So the normal force. And the normal force is along the perpendicular forces. Okay. So any question about this one here? Well, you'll be encountering this type of question, again, inclined surfaces. So remember that the common mistake by students here is that they try to assume that the weight is equivalent to the normal force. But that is only true if your object is lying on a horizontal surface. It's not inclined. Okay. Any other question with this one here before we move on? None. So hopefully, again, you can make sense on how to break them down here, especially the location of the angle. Because if you mess that one up, well, obviously, you're going to interchange also the value of your perpendicular force and the parallel force. So make sure that you locate that angle. The usual is that you'll be given this angle here, but that is the angle from the horizontal, like the inclined angle of inclination. Well, I don't know if that's the angle of inclination, but again, it's usually it's given the angle between the horizontal and the incline. That's the usual case. Okay, so maybe we move on to the next one. So this is what I've talked about, like weight scales actually tell you the normal force. So again, if you're pressing on something, that something will press back. So essentially for most scale, like but your Buttram scale, well, they use the third Newton's law there. Again, the normal force is just the reaction force, okay, by the surface. It's just the reaction force of the surface. So take note the scales, the weight scales gives you the normal force, okay. So in most situations, this is the same as your weight. The force of gravity is balanced by your normal force. Again, uh, you're pressing down the floor because of your weight, okay? Because of your weight, your Fg, so therefore you're trying to press down the surface. But if you're just lying horizontally, if you're not moving or anything, well, that is true. But in a case, this is an example, when an elevator accelerates up or down, okay, that is no longer the case. And accelerates up or down, so it's no longer the case. If the elevator accelerates up, the apparent weight is greater than normal. Okay, that means that if you are not moving, well, you should be, if you want to know your actual weight, you need to go to a Buttram scale that is not moving, okay? Or if it is moving, it should be moving with a constant velocity, okay? Acceleration is up if the net force is, if you can see second Newton's law, the direction of your acceleration is the same as your net force, okay? So therefore, it's also up, second Newton's law. Second Newton's law. Direction of acceleration is the same as F net, or the net force, okay? So if the net force is up, so acceleration is also up. So if the acceleration is down, the net force is also down. Again, remember, I couldn't emphasize this one, that when you say net force, it's the sum of all the forces. So when you say F net, sum of all forces acting on a single object, on an object. Again, this is only applicable for first and second Newton's law. Like the forces are acting on a single object. So therefore, if you want to use the first and second Newton's law, you just try to concentrate on one object, okay? So I'm gonna show you a particular video. Well, if you have a chance, although make sure that you are not disturbing others. Like if you have an elevator, if you're living in a high-rise building or what, you can try this one out. I tried this one last night. So let me just see if I can download that. So maybe if if you can tell me what you observe. Well, actually, this is me taking an elevator going up and try to observe what happens, or what do you observe? Window. Okay, can you see that one? It should be a video file. Can you see that? Anyone?
Yeah.
Okay, so this is me, well, taking the bottom scale, and so let's see. And then in this particular case, I'm just was just try I only tried if I'm moving up. So see what observe the dial in the bottom scale. The start. See what happens when it stops. Oh. Okay, I'll leave it on. Try to observe in the lighter part, this section here. So in that particular part there, what do you observe? So can you see any difference in the reading? Anyone?
Yes.
So what happens? Again, at the point, that was when I was already closing to the second floor. So it almost stops. So what happens to the reading?
It quickly increased.
And actually, I think it's the reverse, right? Somehow decreased and then went back. Let's see again. If you can see here, my reading is around close to 140, and my was about to stop. So if you can see, the dial went to close to 120. So that means that there's a particular decrease in, well, if this is the weight that is being given by the bottom scale. So you can also try this one in your, well, if you have the chance, but make sure that you're gonna do it in particular time that no one uses the elevator. So you should be expecting, although it was not really shown in that particular video, that at the start there should be a difference in the reading. If that is close to 140, there should be actually an increase if it's moving up. But eventually, well, in between floors, your elevator is moving with a constant velocity. What happens there is that if it's moving with constant velocity, the reading will give you the actual weight of your body. But later on, if you observe, upon going to the second floor, or before it stops, actually there's a decrease in the weight. So the reading. Remember that the reading of your bottom scale is the normal force. Okay. So indeed, there would be a difference in reading if somehow, if you're doing this measurement in a particular place that is accelerating. Okay, if you're accelerating, you should expect that the the reading of your bottom scale is different. So if I just gonna go back to, where was that? To the notes. Okay. Okay. If based on this here, if you're accelerating up, the net force should be up. And if you're gonna examine what are the forces on the, so don't think of the whole thing, okay? We're just up to, because the bottom scale is acting on the person. So you focus yourself on the person. So this is the person, okay? And if I'm gonna examine what are the forces acting on the person, well, this one here, this is accelerating up. So the meaning of this one is accelerating up. So if it is accelerating up, that means that the net force is also up. So if that is the case, well, I know that there are two forces acting on my object. One will always be gravity, that is Fg. The other one is the normal force. But in this case, since the net force is up, that means that in this particular case, if you're accelerating upward, I would expect that the normal force is bigger. Okay, so in this case, the magnitude of Fn is bigger than the magnitude of my Fg. Okay, why did I say that it's bigger? Well, the net force is going up, because the net force, if I'm gonna get the net force, F net, since the acceleration is moving up, that means that F net is also moving upward. Okay, again, how do I know that one? Because acceleration is up, so net force is up. So again, if the acceleration is up, net force is up. So in the second drawing, again, if this is the person, well, the person is only acted upon by two forces here. I have Fg that is directed downward, okay? And if you can see, the acceleration is going down. Well, which tells me that the net force, so acceleration is down, that means that F net is also down. So that means that for my net force to be down, that means that the normal force, Fn, is smaller. So in this particular case, if the object is, or if you're riding on an elevator and then you're accelerating downward, your weight, the magnitude of your weight is bigger compared to the magnitude of your normal force, or the normal force being exerted by the scale. Okay, so that means that F net here, again, since the acceleration is moving down, that means that net force is also down. So that means that Fg, so therefore F net is down. In this case, the other one, therefore F net is upward. Okay, so first is F net, again, acceleration is down, so that means that the net force is down. But if there's no difference between the normal force and Fg, well, that is your actual weight. And that only happens if the bottom scale is not moving or moving with a constant velocity. So any question with this one here? Again, we're talking about the person. That would be our object, okay? And the person is acted upon by two forces. One is the force exerted by the surface. And since the person is on top of your scale, okay? Top of your scale, that means that that is your normal force. And again, the weight scales or the weight that you read in your scale is just the normal force. Okay, so this is the reading again, reading. So this is the reading that you see in your scale. Reading you see in the scale because it uses that particular concept, the third Newton's law. And again, this one here is the reading. The reading you see in your scale. So any questions or clarification in this case? So again, maybe I'm just gonna take note here that the scale reading and Fg is equal. So in this case, your Fn, the magnitude of your normal force, is equivalent to your Fg. That only happens if A is equal to 0. Okay. So again, if A is equal to 0, it is either at rest or constant velocity. So zero acceleration doesn't only constitute an object that is not moving. It can also move, but specifically moving with a constant velocity. Okay. Any question with this one here? This particular part? None?
Nope, we're good.
You're good. Okay. By the way, William, right? Let's see.
Mm-hmm.
I think I checked if
Yeah, I came late.
mhm.
My bad.
It's all good. Okay, everyone is here, so you're all good. Okay, let's take this example and then we'll have a break after this. Okay, so Marlo is standing on a weight scale in an elevator traveling up to his agent's office. Starting from rest, the elevator accelerates upward at 2 meters per second squared for 3 seconds and then continues at a constant speed. If Marlo's mass is 60 kilogram, what will the scale read during the acceleration? Well, again, you only have a difference in reading when the object, if you can see here, there are only two cases. If you're accelerating upward or accelerating downward. If the object or if you're now moving with constant velocity, that means that the net force acting on you is 0. And in this particular case, there's only two forces acting on Marlow. It's either the normal force and the weight. Okay, but the question is specifically asked as what would be the reading during the acceleration. That means that for when the acceleration that happens for 3 seconds, okay, and then continues at a constant speed. So in that particular case, if the object is already moving with the constant speed, you would expect that the whatever is your normal force would be the same as the weight of the object. Okay, so if I gonna draw my free body diagram, so for any dynamics question, especially for if you're gonna apply the first and second Newton's law, you start your solution with free body diagram. And again, what is your object? Well, in this case, it's Marlow, because you're trying to get the weight of Marlow. So you're not looking at the elevator itself. Well, if you're gonna focus on the elevator, there are other forces there. But again, we're just focusing on Marlow. So that means that this is Marlow. We represent Marlow as just a point. Okay? We're given that the acceleration is upward. Sorry. So that means that A is here, upward. So here's the thing. For dynamics questions, actually, it's much easier if you're gonna take the positive direction wherever is the direction of your acceleration. So therefore, in this case, since it is going upward, the acceleration is upward, so I'm gonna use that going upward is my positive direction, and then downward is my negative direction. Okay, so again, for dynamics questions, it's much easier, again, in the calculation, that you're gonna set your positive direction the same as the direction of your acceleration. So anything that is upward in this case, I will set that one as my positive direction. So now, going back to the free body diagram, I have two forces, Fn. I have two forces, the normal force, and again, in this case, this is just the scale reading. And I have my weight, the weight of Marlow, which is represented by Fg, which is equal to mass of Marlow times acceleration due to gravity. And if you can see, I draw longer normal force because I know that the net force should be going up. Again, how do I know that one? I know that one because the acceleration is moving up. So that means that the net force is also going up, or that means that if I only have two forces, the force that is moving upward is bigger compared to the force in the opposite direction, which is in this case your weight. Okay, so now there are only two forces acting on Marlow, and that is my normal force and Fg. So we're gonna take note the given quantities that I have. I've given A is equal to 2.00 meters per second squared, and again the direction is up, and my mass is 60 kilogram, mass of Marlow, and And again, since our object here is Marlow, and the second Newton's law talks about the object, specific object, so we're talking about the mass of Marlow here. Okay, so now it has an acceleration, so therefore we use second Newton's law. The second Newton's law tells us that the net force acting on the object is equivalent to its mass times its acceleration. Okay, and I set my moving upward as positive. And if you can see what are, well, again, this is the sum of the forces. So if I can expand this one, so make sure that you follow this format. There are two forces acting on the object. That means that I'm gonna sum them up. And if you can see, they're just on the same component, vertical components. So therefore, I'm just gonna use upward as positive. So that means that I have positive Fn. So that is the upward force, plus Fg is in the opposite direction. That means that its direction is negative Fg, is equal to Ma. Again, I'm just trying to expand my F net, or I'm just trying to get the sum of all the forces. Again, the meaning of this is you're taking the sum, taking sum of forces acting on object. Okay, so therefore, if you can see, that's how you use your free body diagram. If you can see, there are two forces, Fg and Fn. Okay, and remember that you're solving for Fn in this case, scale reading. So this is just again your Fn. So that means that if I'm gonna solve for Fn, Fn is just equal to mass times the acceleration plus. So if I'm gonna transpose that one to the other side, that is just plus Fg plus Fg. So the normal force is the sum of Ma plus Fg. Or if I'm gonna expand that one out, or I'm gonna substitute my values, M is just 60 times the acceleration of 2 plus Fg is mass times 9.8. Okay, so Fn therefore is equal to so this is just 120 plus 60 times 9.8 is 588. Okay, so that gives you Fn is equal to 708. Okay, so the scale reading is not your actual weight. We actually call this one apparent weight. Scale reading is 708 newtons. Okay, so this would be the scale reading, 708 newtons. So if you can see, this is your actual weight. This is your actual weight. But since the elevator upon which you are in, along with the scale, is accelerating, well, you could actually feel that one, like the top of the Wattrom scale will be pushing hard. You can feel that one in your feet, that somehow there's someone pushing you harder in that particular case. So the harder the push, that means that there's an increase in the normal force. Okay. So in this particular case, well, that's the main question. But if we can extend it, let's say this is just an additional question. Okay, it's not part of the actual question. Like, let's say, for example, if you will be asked, what is the scale reading after 3 seconds? So what do you think? What do you think is the scale reading after 3 seconds? Anyone? Can you give me a number? Or do you need to solve, or no need? Or can you find the answer with the previous answer that you have? What do you think? Anyone? Any idea?
It doesn't stop, right?
Yeah, it's still moving.
So wouldn't it stay the same?
Yeah, why do you think so?
Because in the video, like that you recorded of yourself, the scales, like the weight of the scale stayed the same until the elevator decelerated and stopped.
Okay, great. Because after 3 seconds, it says that speed is constant, right? It's constant or still moving, but in the same direction, or that's the same thing as velocity. Velocity is constant. So if it says that the velocity is constant after 3 seconds, that means that A is 0 after 3.0 seconds. So if A is 0, that means that the net force is equal to 0. There's, again, net force is equal to 0 doesn't mean that there's no forces acting on the object. Well, actually, if you're going to go back to your free body diagram, if this is Marlow, there are still two forces acting on the object, which is Fg and the normal force. Okay? But since the F net is equal to 0 and there are only two forces that are moving in the opposite direction or directed in the opposite direction, that means that Fn is just equal to Fg. Okay? Because if you're going to expand this F net is equal to 0, that only means that positive Fn plus your negative Fg is equal to 0. Okay? So that means that the magnitude of the normal force is just equivalent to your Fg, which is 588 newtons, which is your actual weight. So that means that in this particular case, you'll get your actual weight. Any questions?
I just have a question about the free body diagram.
The first one or this one?
This one.
Yes.
So do the dashes across the arrows mean that they're
They're
equal?
equal in magnitude.
Okay.
Yeah. So usually in math also you use this symbol here to denote same length. So that means that, yeah, the length of the lines there are the same.
Okay.
Yeah. I'm not so strict if you're gonna draw your free body diagram, especially if it's accelerating and you just draw it like more or less the same length. I will not be so strict with that. But it's better to actually also draw your free body diagram that is closer to the actual thing. Okay. Okay, so uh, can we have a break? So we will